Let's look at number 4. So if we look on the paper, it says the population of Arizona is one of the fastest growing in the country. The table and graph below gives the population of Arizona at various times over the past century. So if you look at this, it says time since 1920 in years. Well, if there are no years since 1920, that has to be 1920. So the first coordinate is like in the year 1920. Then 20 years later will be 1940, 1960, 1980, then the year 2000. And then we also want to look over here at the graph at letter A. Number 4. Is this a linear or an exponential function? Which one would be a better match for this pattern of population growth? Explain your reasoning. So if we look at this pattern, we can see it's not a constant rate, it's an exponential rate. So it's exponential growth. It's not a constant rate. And now let's look at B. Use your calculator to write a model that could be used to predict the population of Arizona for any year. What does your model indicate about annual population growth in Arizona over time? Okay, or over this time period. So what we're going to do is we're going to use our calculator, the numbers, the data. So in L1, we're going to put our data under there for years. In L2, we're going to have population. It's done just like you did your linear regression. Stat edit. And then after stat edit, what would you use? Right, you put in all your numbers and then you go to stat calc, but we're not stat calc. We are not calculating linear regression because we said this is exponential. So you cursor down until you see exponential, REG, okay, for regression. And then that's where we will be able to find out what our equation is. We'll hit enter until we see our A and our B, and then we'll plug in. So now I'm going to pull up the calculator. It might show over there. Let's hope it shows over there, and then I won't have to erase what we've already done. So let's do that. We're going to put in, we're going to stat edit our exponential regression equation. But we do know our data points. So we start with 0, and then we put in, we hit enter, then we put 20, enter, 40, enter, 60, enter, 80, enter, and we have that. Now we go over to our next column and we put in 0.334, enter, 0.499, enter, 1.302, enter, 2.718, $5.131, and we enter. So we have our data in, but we want the calculator to do the work for us. So we're going to do stat calc, and we know this is exponential, so we cursor down. Oops, too far. There it is, right there. So now I'm going to hit enter. And I need to hit enter again, and now I have what I need for my equation. And let's round it a little. So let's put our equation in. Let me go ahead and I'm going to pop back over to the worksheet. And we're going to round some. So our equation is y is equal to 0.298, that's your A, times B. For B, let's use 1.036. We're going to round it in that way to the x. So for any year, we can use that. And all we have to do is change x to the time, depending on what year we want to do. So now let's look at D. First of all, let me make sure. Oh, we need to finish C. Use your model to predict the population of Arizona in 2010. So actually, here's where I should have put the model. Y is equal to 0.298 times 1.036 to the x. And then 2010, we want to know what year that's going to be. Well, we know that 2000 is where we have 80. So it looks like we go up 20, so if I went to 2020, it would be 100. But I don't want that, I want 2010. So what we're looking for is when our x is 90. So 2010 actually corresponds to 90. So we are actually looking for the value when we have x is equal to 90 for 2010. So you can either look on your table and find that, or you can plug it into your calculator. Let's see. If you plug it in, you just go ahead and put that in. 0.298 parentheses, 1.036, close your parentheses. Use your caret symbol. So you're putting in 0.298, 1.036, this symbol, and then the number 90. And then let's see what we get. Okay, so it's 0.298, 1.036. Okay, let's round it to 7.2. Because we have 7.18777,131. So we're going to say 7.2. Remember, that means 7.2 million would be our population in 2010. So that's letter C. So letter D asks us, in what year does your model predict that the population of Arizona will first reach 8 million people? So now what we can do, we have a plan. What you can do is you can actually take this general equation, put it in your y equals, and then go down your y column and see where you end up with 8 point something, because that represents the 8 million. So let's go ahead and do that. We're going to put the exponential regression equation in our y equals. So let's clear this history. Well, here, I'm going to put it like you all did. I'm going to round it. 0.298, because it'll change if we don't round it, times 1.036 to the x. And then we can look at our table, but one thing we'll notice is our table starts all the way at 0, and we want to go up at least, we know we want to go up at least to 90, because we just came from 90, and that was only 7.2 million. So now I'm going to show you how you can start your table wherever you want it to start. You hit second window, and that will allow you to start the table anywhere you want to. So let's start it at 90. And now let's look at the table. Second graph. So in 1990 we see our 7.2, approximately 7.2 million. So now we want to see when we first hit 8 million. If we notice, it's right here at 94 where we hit 8.2801 million. So it would be 94 years after 1920. So let's get all that figured out. Let's pop up the calculator, the worksheet. So 94 years later. Well, 90 years later is 2010. So that means we need 4 more years, so it's going to be 2014. And at that time, we saw the population was at least 8 million. I believe it was 8.2. But at any rate, we know this is when it first hits 8 million. Okay, now we're going to move on to number 5. Okay, so let's look at 5. Duncan's grandparents put some money into a college savings account when he was born. They intend to let the interest accumulate in the account until he needs to use the money to help pay for college. The rule y equals 3,000 times 1.06 to the x gives the account balance after x years. So they actually gave us the rule. Now they're going to ask us some questions based on this rule. How much money did they put into the account when Duncan was born? And explain your reasoning. If you said $3,000, very good. Because when we have y is equal to a times b to the x, we know that a represents your initial investment, your initial amount. Good. What is the interest rate for this account? 6%. Good job. Because we know that in this situation it is growth. So we have y is equal to a, and b can be found by 1 plus the rate or 1 minus the rate. But in this situation we have 1 point something, so it's greater than 1, so we know it's growth. In order to get that 1.06, we have y is equal to 3,000 times 1 plus 0.06 to the x. Because remember, that's that 100%, that's a decimal of 1, and that's 6%. So 6% as a decimal is the 0.06, and that's how we know that it grew by 6%. How much money will be in the account after 18 years? So you have to decide, where does the 18 go? Right, it goes in place of your x, equal to 3,000 times 1.06 to the 18. And so let's plug that in the calculator. You could also put the equation in, but this is quicker. To the 18. Good. 8,563,002. So that is what we'll put down. 8,563.02. Describe how the account balance changes over 18 years, over the 18 years that the account is open. So the account increased by 1.06 every year. So the account balance increased by a factor of 1.06 each year. Okay.